Okay, so this is the video associated with the Factorial ANOVA. I'm going to show how to use the code, how to produce a plot, how to look up AP or how to write up APA style, and we'll go through this together. To best follow along, you're going to want to download the code at some point and be able to run it on your machine by also downloading the CSV file called Factorial .ANOVA _ data, I believe, and also changing your working directory. So let's go ahead and see how to do this. Okay, so here is the code. So this is, again, an example of a Factorial ANOVA, and you want to make sure that you have this data set here downloaded and in your directory, and you want to go ahead and make sure that you have changed this particular directory to wherever you have stuff saved. Other thing I would say is here I've made this echo false command so that we can suppress the code in the output so that it looks a little prettier. We have a few more extra libraries here, specifically scplot will want for the graph. So our graph's going to look a little bit different here. So go ahead and make sure that you install these beforehand to get the most out of this. Okay, so let me go ahead and set my file up here. And here's an example of a question. So we're going to ask, whether the type of computer, a Mac or a PC, and whether someone is living alone or with somebody else impacts the number of hours per day that people spent looking at a computer screen. And here I just simulated some data. So again, this is fake data, so we know that what it comes out. But the idea is that we have two independent variables, the type of computer and the living status. And there's two levels of each, a Mac and a PC, and alone or with others. So this is a 2 by 2 ANOVA. And our dependent variable is the amount of hours per day people spent looking at a screen. So we're going to run this, but just remember that when you have more than one independent variable, we want to do a factorial ANOVA. And we could have more levels of each, but this is kind of the simplest design with which you can build out. Okay, so first thing that we're going to do is we're going to bring in the data. So we've done this many times. We'll just hit Control Enter. And now we'll see over here that we have 200 observations. There's 4 different variables. There's an ID, like a participant number, a computer type, a living situation. Both of those are factors, and then the number of hours of screen time they have. So you can see all of those right over here, and that'll go ahead and help you know what's in that data set. So the first thing that we're going to do is we're going to calculate some descriptive statistics. We don't need all of these things necessarily. That being said, it's helpful for reporting, or if you want to add these into other calculations later or something. So we're going to calculate means, standard deviations, and standard errors of the mean for each cell, okay, and overall, and by each independent variable. So what I mean by that is this whole first section here, this is all averages. There's my great spelling, that's certainly wrong. Averages for the overall average, so this is the first line, the grand mean, so to speak, is the average of screen time, ignoring everything else. The next thing we're going to do is we're going to calculate averages for the potential main effects. So here, the average for IV1, and here, the average for IV2. So here we're just saying, look, aggregate, meaning compile together, screen time as a function of living or computer type on the data, and what function do we use? The mean. Okay, so here, each one of these is saying, look, we want to aggregate in different ways a particular function on a particular set of data. So here we're going to have data being the same and mean being the same for all of these. And we're going to do the same thing for the standard deviations here. Okay, so here we're just saying, well, if we ignore all the variables, what's the overall mean standard deviation? Within Mac versus PC, what's the mean standard deviation? Within living a home or living alone or with others, what's the mean standard deviation? And then what is the mean and the standard deviation for each individual cell is the last one. So here, in order to do each individual cell or each permutation of those variables, we just have to add this here, where we say both. Okay, so in this function, we have screen time and then a little squiggly line as a function of our IV or our multiple IVs. And you could do that all the way to as many IVs as you wanted. Okay, so as your design got more complicated, you could use this code to do that. The other thing that, and so let's just go ahead and run this, and I'll show you a couple examples here of what it looks like. So we can highlight everything and hit Control Enter, and that will run that specific chunk or specific highlighted portion. And then let's just look at the cell standard deviations as an example. And what you can see here is as a function of each particular permutation or combination of the independent variables, we have a particular value for the standard deviation. So this is just a way to get all your numbers kind of in a form that you can access them later. The next thing we're going to do is we need to figure out standard errors of the mean. And in order to do that, we need to figure out how many examples or how many observations are in each place or each cell. So we can use this function called xtabs here to do that. And what we're going to say is, okay, well, tabulate the number of different observations as a function of computer type and living arrangement, and do that on the data variable. So if we do that, that's going to tell us what our sample size is for each. And if we look down here, we have this nice balanced design where we have 50 people in each cell, and we can go ahead and put that number in for the number of observations per cell. Now, if we had an unbalanced design, we'd have to do this a little bit differently. That's okay. It's still going to tell us those things. We would just have to put a number in here for n instead of doing it over when they're all exactly the same. So we just change our code a little bit. Okay, so now we've done that. We said, okay, great. Here's our xtabs. We know that their number of observations per cell is 50. And now we can calculate standard errors of the mean by just taking those values that we've created already, the cell standard deviations, and which particular number in that cell we want, and the number of observations here. So we're calculating standard errors of the mean, and we're just simply using this code that we did above to make sure we have those calculations. Okay, and often you'll want to do this just to have your descriptive statistics somewhere. Okay, so no real output at the moment, just getting set up to tackle these different values. Next thing we're going to do is we're going to conduct the ANOVA test. And this is going to look very similar to a one-way ANOVA with one difference. We're going to actually add this interaction between the two variables. So before we just had one, we had our, sort of our DV squiggly line IV comma data. Well, now if we have more than one, we can just add those together. So here, what you'll see is we want to know what screen time is as a function of little squiggly line, computer type, living, and the interaction of those. So anytime we do an interaction, we put a colon in between. So this might be IV1 and IV2. And this is going to be interaction. Okay. So we're just adding one extra term in here. So let's go ahead and run this. And I also put a reminder of that right there. So you have it for later. And now what we'll do is we'll go ahead and call this results, and we'll go ahead and do a summary of it, just like we have in the past. And we're going to again get our ANOVA table. And what this is going to tell us is all the information we need, or most of the information we need for reporting. So again, this is set up like a one-way ANOVA where we have our independent variables over here. We have our degrees of freedom for each one of those independent variables and the overall residuals. We have the F value for each one of those, and then the associated P value here. Remember that this PR greater than F really is kind of like a hint at what we're doing, right? Remember, an F distribution looks something like that. And we want to know the probability of finding our F value larger than that critical value. Okay, so you can, even though this doesn't say P value, remember it's the probability of finding an F value greater than that critical value. Okay, so here we want to look for those as being less than 0.05. The stars are cues for that. So here we have no effect of COM type, but we have yes, an effect, significant effect of living and the interaction. Okay, so remember for factorial ANOVA, main effects are IVs independent of each other. Interaction effects are IVs together in some combination, okay? So what we don't know yet is we don't know what that interaction effect is driven by, and we also don't know how big the effect is. That's great, we've got some code to do that, so let's do our effect size, and that's gonna give us eta squared, bang, bang, boom. Notice here that because we have more than one independent variable, the difference between eta and partial eta squared is actually different. Before, those were the same for the one-way ANOVA. Remember that because each independent variable contributes a part, we want this partial eta squared. Okay, and we can literally think of only the ones that are significant as mattering. So we know that computer type wasn't significant. So you might want to just think of that as like crossing that whole line out. And these are the effect size that we're going to use. Okay. Now, so we know, great, we know our effect sizes, we know our main and interaction effects, but what we don't know is we don't know what's driving those interactions, like which cells are different from each one. Same thing that we did in a one-way ANOVA and a t-test. We want to just see what's driving that. We'll do this with these post-hoc tests. This is a little bit different than how we did this in a one-way ANOVA. So just notice that this is slightly different code here. We're going to use Tukey's HSD. Post hoc test, there are many different kinds. This is a good starting place to give you a decent look at your results without going into too much depth between all the different tests. Again, it makes a correction for the many tests that we're going to do. So let's run this and spit it out so we can see it. Notice that there is quite a large table that comes out. Okay, here, our main effects only have 2 levels, right? We don't have 3 levels, so they only have a difference between one level and another level within each. Let's say we had PC, Mac, and Linux. You might also see PC to Mac, PC to Linux, and Linux to Mac, right? Just like in our one-way ANOVA, we have many comparisons. So you can do your post hoc tests here on both the main effects and the interaction effects with one command, which is really, really nice. Okay, and another thing we should also notice is that this adjusted p-value here is exactly the same p-value that you would have gotten in that F table, that original ANOVA table that we ran, because there's no post hoc tests to do on the main effects. Okay. That being said, if we look down here at COM type to living, the interaction, so this is all interactions, all the interactions here. What we'll see is that there's a nice right here, this tells you the comparison we're making in this row. This is going to tell us our difference and our confidence intervals. Let's just ignore those for the most part now. And we really care about this adjusted p-value. So here we're going to say, all right, is there a difference between PC alone and MAC alone? And that p-value is 0.67, blah, 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 blah. Okay, so that's bigger than 0.05. Let's clear this. This is bigger than 0.05. So that means non-significant. Let's look at MAC living with others versus MAC living alone. Ignore, ignore, ignore. This p-value is less than 0.05, so this must be a significant difference. And we can do this for each one of the rows as they go down, and that will tell us what's driving those effects. Okay, all the interaction effects. So remember, up here, main effects. Down here, interaction effects. Notice also that when it tells you which one we're looking at, because we have called this a particular variable, right? We've called this post hoc right here. What that means is that I can then go in and I can say, hey, look inside post hoc with the $ for com type, and then it can give me this p-value. So I could call those later or something like that if I want to. And you'll see this down here in the write-up momentarily. Okay, so this is how to read that table. Next thing we want to do is write it up. So typically what we do is we say the particular type of design, A2, what that is, computer type, by 2, living situation, ANOVA. Remember the 2 and the 2 refer to the levels of the independent variables, PC, Mac, and alone versus others. And we just summarize that in a screen, blah, 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 blah. Then the next sentence here, we want to tell the main effects first. So here we had a main effect of only the living situation. And we can go ahead and put that in. Here's our F, our residuals. We did some of this in code. Some of it I just wrote in here because I think that's slightly easier. It's not quite as easy to just pull those things in from results as in others. The partial eta squared, though, I also did in code as well. And our computer type failed to reach significance. I put the p-value in there. Not everybody does that. I like to give more information rather than less. So the again, if something isn't significant, we want to say failed to reach significance is a nice term to say that. We also want to talk about the interaction effect. So here we're going to say, okay, well, the interaction was also significant. This is our F values, our P values, our partial eta squared value. And remember that those values come from here. We run this again, our summary of results. So here we have a, this 8.174 can be found right here. The p-value 0.05 can be found right there. For the first one, 54.278 right there. So we're always looking in this F value and p-value area of this ANOVA table to get those numbers and write them in. Okay, and then lastly, what I said was, post hoc tests revealed significant differences across all the cells except for the one that was non-significant. So this is a little bit simpler than trying to list out all the things. And we're going to make a pretty picture of this here in a moment. But remember that this is coming from this table where we say not significant, 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 significant. So here I just summarized that in this last sentence by saying everything was less than 0.05, except for that first one. And that's a perfectly acceptable way of doing that as well. So let's make a picture. Here we have figure 1, and maybe I'll give this a some kind of title: differences between PC, Mac users and living alone or with others. And we might say differences in screen time or something like that. Whatever you want to say here, you know, we can address those, or we can adjust that kind of however. And what we're going to do is we're going to also remember just to put some kind of note at the bottom of it that tells us what these are. The way that I've written this is that we have 95% confidence intervals for the error bars. That's just a little bit easier to code up than using standard error of the mean. Does the same kind of thing. So here for these slightly different graphs, this is just a slightly easier way. Okay, and so what we're going to do is we're going to use this function called lineplot.ci. This is in that scplot. And what we're going to say is, all right, well, what is our X factor? Well, it's the data, the computer type in the data. We could also we could switch this with living. It doesn't really matter how you do it as long as it's one of the independent variables. So this is an IV. And then we want to say response is really the DV. So this is screen time. Our grouping variable is the other IV. So you could potentially switch computer type and living. It's just these two are pretty interchangeable. This is a balanced so that it has 2 and 2 levels. If you had 3 groups, you might want to change that slightly differently. It just sort of depends on how you want to display it. And then the CI function, that's just our confidence intervals for our error bars. And this CI mean calculates the confidence intervals for us and makes that the error bars. So again, a much simpler way to plot. And then I added some labels in here that you could change later. Okay, so let's see what this looks like. If I play this, we get this very nice, pretty graph where we have one IV here, another IV on the bottom, and we have 2 different types of, in our screen time over here, and we have 2 different types of lines to see differences between the 2 groups. And remember, because these are confidence intervals, we can really sort of like imagine lines this way and lines this way to see what overlaps, and that tells us a little bit about what is significant versus not. So if the lines end up crossing, remember we have an interaction effect. To remember to think of those going out like all the way to infinity, but this looks about right. So let's see what this would look like outside of R, so that if you wanted to send this to somebody, you could. So we'll hit Control-Shift-K. Control-Shift-K. There it is. And we're going to get this nice HTML file here. I've left some of the output here so you can see where all those numbers go. And then we also have the written write-up where, you know, we have all of our numbers in here. Partial eta squared equals 0 looks a little bit wrong. We might want to come back to that because it shouldn't be 0. It should actually be these numbers up here. So I must have written that slightly differently, but you can look at that. It's probably rounded incorrectly. Okay, so and then again, all the way on the bottom, we have this nice, pretty graph that has our title, our mostly APA formatted graph, and a note down here at the bottom. Okay, so now using this, you should be able to take this and adjust it such that it fits any kind of design for you. So this is the end of the basic factorial ANOVA. Again, make sure that if you have any questions or you don't know how to use it, I am always around for help for class or for others just watching. Thanks.